All right, Big Ideas Algebra 2, Section 9.2, Angles and Radian Measure. So we're going to be able to look at angles in their standard position, find coterminal angles, and use radian measure. So typically we have been looking at angles only in degrees. Radians is going to be another unit that we're introducing. But first, how you line up angles within your two different sides and where your vertex goes. So in a coordinate plane, your angle needs to be formed by fixing one of the rays or one of the sides called the initial side, and then rotating that other ray called the terminal side around the vertex. An angle is in its standard position when the vertex is at the origin, at the coordinate point 0, 0, and when the initial side is on the positive x-axis. So this diagram has it set up perfectly in its standard position. Notice that your vertex is at the origin right here. Your initial side is on the positive x-axis, so on the right side of your y. And that terminal side, wherever you want that angle to end up, is being rotated around the vertex, and wherever it ends up is what you are looking for. Notice that where we are starting is at 0. Straight up would make a 90-degree angle. Complete opposite side for a straight line, 180 degrees. Then continuing down is 270, and then if you end up all the way around back where you started is 360 degrees. We're going to continue using these major four quadrants and kind of breaking those up into a little bit smaller pieces later on. So first, let's just kind of draw an angle where it would look like in standard position. So because 240, the next biggest one is 180, you know it's going to be between 180 and 270, but the difference from that 180 to 240 is 60 degrees. So you're going to draw your terminal side counterclockwise 60 degrees past that 180. 500 degrees. So you can rotate farther than 360 degrees. So it is going to be between the 90 and the 180 sides, since you're taking away 500 to 360 to get 140. This is between 90 and 180. So that terminal side is going to be in the second quadrant, or in the left side of the X, but above the X. So you're going to do 140 degrees more for that counterclockwise rotation. You can also have negative degree measurements. So because negative 50 is in the negative position, the terminal side is going to be 50 degrees past in the opposite direction from that x-axis. So you're going to go down from your initial side 50 degrees. All right, converting radians to degrees. I actually had these out of order, so let me switch on over to how to convert. So your angles can also be measured in radians. A radian is just another unit to measure angles. A radian is equal to the measure of in standard position where the terminal side intercepts with an arc length of r. So a radian is just another way to say radius, whatever the distance of that radius is. 1 radian is what you would get if you take that radius over 1 unit. So because the circumference of a circle is equal to 2 pi r, there are exactly 2 pi radians in a full circle. Again, think of radians as a radius. And if there is 1 radius for a circumference times 2 pi, there are 2 pi radians in a full circle. So you can think of it as, you know, a full circle is 360 degrees. That is equal to 2 pi radians, or half of that, to divide both sides by 2, 180 degrees is equal to pi radians. Down here at the bottom is going to be your kind of conversion formulas. So if you were going to try and convert degrees to radians, you're going to multiply that degree measure by pi radians on top and then divide by 180. If you were going in the opposite direction, trying to convert radians to degrees, you're going to take your radians measure times 180 and then divide by pi radians on top. You do this so that you're going to have your pi's cancel on top and bottom for the second one. And then for the first one, you're going to have a pi left over since you're being converted into radians. Most of the time, your radian measure is going to be listed in units of pies. Sometimes you're going to be writing it out in decimals. It just kind of depends. So let's go back to that last slide. So converting from degrees to radians, and then from radians to degrees, whatever you're given, you're just going to be converting to the opposite. So A, we're given this degree symbol, so we know that we have degrees to start and we need to convert to radians. So in order to convert, you're going to multiply by radians on top and then degrees on bottom. So 120 times pi divided by 180. Notice that your degrees on top and bottom cancel with each other, so you're left with the unit radians. 120 over 180 needs to be simplified. You can first cancel out the zeros, so you have 12 over 18. And then you can divide both the top and the bottom by 6 to get 2 over 3. And you are left with pi because pi cannot cancel out with anything. Now converting from radians to degrees is the opposite. So you would multiply by pi on bottom and then 180 on top. Your radians cancel with each other. Same thing with your pies. Your pies on top and on bottom cancel with each other. So all you are left with is 180 divided by negative 12, and that gives you a negative 15 degrees for your angle. All right, positive and negative angles that are coterminal. So in order for angles to be coterminal, they are lying on the exact same position. So we've talked about how you could continue rotating this angle all the way around, really infinity, and you're going to have different angle measures. So like 0 and 360 are coterminal angles because it's your starting and your ending position. 90 and whatever 90 plus 360 is, so that would be 450 degrees are coterminal. So you have multiple different angles that are coterminal with each other, or they are lying on the exact same position. So when you draw out your starting, your initial side and your terminal side, all you're pretty much going to be doing is adding or subtracting 360 from both of these. So when you find the positive angle that's coterminal, you're going to be adding 360 to this. And then when you find your negative coterminal, you're going to be subtracting 360. So that's it. So 315 is coterminal to negative 45. And the negative version is when you subtract it, you get negative 405. And they end up at the exact same line. Same thing with 395. You're going to subtract 360 to get 35 degrees. And then to find a negative angle, we need to continue subtracting or do it again, because the first time we subtracted, we got a positive angle. So one of your answers needs to be positive, one of them needs to be negative. And you can just keep doing that however many to get 360, either in the positive or the negative direction, until you get one positive and one negative answer. All right, so here are a couple common angles you need to be familiar with when you're converting from degrees to radians. This is kind of the next step in looking at the unit circle to kind of help you when looking at your radians and your degrees. You're going to need to know your 30, your 45, and your 60 in each quadrant, and you're going to know what they are in radians. So you could always refer back to this slide when you need to convert degrees to radians. You could memorize it if it's something that you're interested in. I know you're going to need to for the ACT, but just for the purpose of this class, if you want to constantly reference back to it and you'll just familiarize yourself with these numbers, these are your common degrees and their equivalent common radians. Remember that the formula to convert is 180 degrees is equal to 1 pi radians, so that's what you have here, and then 360 degrees is 2 pi radians. All right, looking at sectors and arc lengths, so you have a sector, which is a region of a circle made up by 2 radii, that is plural for radius, so you have 1 radius, 2 radii, and the arc of a circle. So this blue area right here is a sector. You have 2 radii that make up the outsides and then an arc of a circle. The central angle of that sector is formed by the two radii. So you have a couple different formulas you need to be familiar with. An arc length is radians times the angle, and then your area is 1/2 the radius squared times that central angle, whether it's in radians or in degrees. So a softball field has a sector of a circle as its field with specific dimensions that make up its radii of the 200 feet, and you have the length of the outfield fence 90 degrees at this corner. So the question is, we need to find the length of the outfield fence given these pieces of information. So you know the dimensions, you know that it's 90 degrees for its sector, for its angle, and you know that each of the radius is 200 feet, or the radii is 200 feet. So we need to find the measure of the central angle in radians, and then use the arc length and area of the sector formulas. So step 1 is to convert our 90 degrees to radians. Remember, the formula is times pi divided by 180. So 90 over 180 reduces to 1/2, which is just pi over 2 radians. Because those formulas that we're going to use for arc length and sector have to be listed in radians. So the arc length, we're going to do the arc length first. So radians times radius times our theta, or our angle in radian measure, which is pi over 2, which we got from up here, and then the radius, which is your 200 feet. 200 divided by 2 is 100 times pi. Now this is one where in a real world situation, you're not going to leave your answer in pi. Always use 3.14 as your pi, and then approximate to the whole number, because everything that you're given in this problem is a whole number. To find the area, you just plug in 1/2 radius squared times your radian angle. So 200 squared is 40,000, 40,000 times 1/2 is 20,000, and then you divide by 2 again to get 10,000. Again, multiplying this times pi to get it into a real world number, you get 31,416. And to make sure that you include those units in feet, because you're given them in feet. So since its length of the fence is a single dimension unit, it's just feet, and an area is a squared unit, so that's why you are listing it in square feet. So that central angle of 90 degrees is, think of it as representing a fourth of a circle with a radius of 200 feet. You're going to multiply, you could think of multiplying whatever your circumference is, if you're familiar with their circumference formula, times 1/4, and you would get the exact same thing of 100 pi, and then 10,000 pi for the same thing. So to check back, if you want to think of two fields of 200-foot sides, you could also think of the exact straight distance as the hypotenuse of a right triangle, or the diagonal of a square. The area of that square would be more than that. So, yep, all of that checks out.